Ines Octoloni, who's the Managing Director at Imrand in Aberdeen. And Ines is also going to be talking to us about an important issue for digitalisation, which is looking at pipework data, and I guess it's maybe a bit different to some of the other topics that we've covered, where it's more focused on the data and the analytics than necessarily the 3D models and so on. But it's a very relevant topic, particularly around improving efficiencies in integrity management. So over to you, please, Ines, if you want to share your screen.
Sure. Hopefully you can now all see that.
We can see it, yes, that's all fine.
Okay, fabulous. So yeah, just a little bit of background about the company. I won't stay on this for long, just for those of you who haven't come across Imrand before. Much of what we do is integrity management, as would be expected for most integrity management consultants. However, we do lean very heavily towards carrying out analysis and the development of technology around data analytics and trying to come up with solutions that inform business decisions. We definitely see this as a technically enabled consultancy, where any of the technology that we develop should make a difference to the way that the assets are run profitably, that compliance and safety is given and will underpin everything that we do. But really, this is about actionable insight and trying to use the data in a way that actually helps improve operations. So one of the things that we've chosen, attack that we've taken with the company is really to try and go after some of the big common problems that have plagued the industry for a long time around issues like optimizing scheduling, or the retrieval of data and data quality issues, or continual monitoring and making and reacting quickly, trying to address many of the key tenets of data quality being completeness, correctness, consistency, and timeliness. And one of the things that we're looking at here in this particular solution that we're going to go through today is very much around data quality and being able to use vast amounts of inspection data that we've gathered over the years. This particular solution that we're calling ADA has become central to everything that we've been doing, and a lot of our other products have built around this. So this particular tool has been on the market for a little while now, and enough that within the company we now refer to this as ADA Classic, and that many of the other tools that we are building around this and will be launching over the next little while are things like ADA Max and ADA Zero and a few other unfortunate soft drinks references. But I'll press on a little bit with this. So ADA in itself. So why is it needed? As I'm sure most of you will be aware that within the industry we've been very, very good at collecting data. We've done that incredibly well for decades, but we haven't been particularly great at using that data. And a lot of that's been because there's persistent doubt over the quality of the data that's been collected, for a number of reasons. That clearly, and inspector error can't be eliminated. We can do everything we can to try and minimize it through training and better techniques, through better data collection, through tablet reporting, and any number of ways of trying to improve it, but there's still that doubt over whether or not the information collected was correct. Because of that, we can miss genuine anomalies in the fog, and really we're in this find ourselves in this unfortunate situation where most would agree that we over-inspect, but we still miss problems, and we fail to identify patterns and hotspots and do the trending that we set out to do when we first started gathering all this data. The reason for keeping it in the big IDMS systems that we have is that we want to. The intent is to trend it and to be predictive, but quite often we just don't get to that point because of this doubt. So one of the things that we're doing with ADA is it's about data cleansing. It's actually getting to the point where we can cleanse and condition this data to make it useful. So that when we're looking at this massive data that we have, it's really made up of three things. We're looking at the trends that aren't visible until we can separate out our extreme data, that data that's behaving differently to the rest of the data set that may cause us some concern, and noise. So really we want to get to that, identify that trendable data and gain some insight from it. And so we do that by identifying the extreme data points, or the extreme values that may pose a threat. Also, they may not pose a threat, but they require information, or there are unknowns. But it's data that we have to act on, something that causes us to look at it, separate it from the rest of the data and understand its behaviour. And noise is the irregularities in the data which pose no threat, that we don't have to act on, but we need to recognise them because their inclusion will skew our trends. So this could be things where we have multiple readings above nominal, which may be correct. They may be on a welder light or something where it is actually thicker, but including that in our trends would skew them and would give us it would mean the output was no longer useful. So when we're looking at identifying these extreme values, these extreme data points, we can think of them in some ways as outliers. But if we thought of them in outliers as in statistical terms, as we normally would, the temptation would be just to disregard them. The problem with that is that within these contexts, they could be correct, and so we can't disregard anything. We have to identify them and we have to act on them. And so really this prompts two actions, either reinspection or a desktop investigation. So that reinspection would tend to be whether the analysis looks like there's a measurement issue, or a desktop investigation where it looks like there's an associated data issue. So that the associated data could be an incorrect pipe spec, or or any of the data that's been recorded for that test point that looks like it's simply incorrect. And once we've managed to identify all these extreme values, all these areas of interest, and manage these separately, then the trendable data is that data that is left. What we're working to do with this, though, is to gradually convert all these extreme data points into trendable data as well, by making sure that we've verified them for their correctness and then include them into the overall data set. So once we've got that to a point where we have a reliable data set and we're working towards it, we can have a wide variety of outputs from this, where we're looking at improving the accuracy of corrosion rates and remaining lives, and start to identify failure patterns and behaviours. And I'll go through some of the outputs from the software that we've developed in the coming slides and show you how that can work. But what's really one of the things that we need to do is to look at it in terms of work done as well. Not necessarily just in the way that the asset's been degrading, but how we're reacting to that degradation. Are we using our resource correctly to control that risk? So if we're finding areas of heightened degradation, of accelerated degradation, are we reacting to that in the right way? Are we looking at the right things? So the software's been developed to look not just at the degradation patterns, but at our reaction to it. So again, one of the advantages with this as well is it's just volume. It's simply being able to crunch a huge amount of data and present that in a way that's easy to understand. That it's simply, when we're looking at tens of thousands of data points and dozens of corrosion circuits, actually for any single person to be able to have a full understanding of the data, no matter how good they are, no matter how well they run their systems, if that information is contained within relational databases, or at best or at worst Excel spreadsheets, actually being able to find insight from that can prove to be very, very difficult. So a lot of what we've looked at is not just the analysis of that data, but the visualization of the output to put it in a format that's easy to understand and easy to communicate the problems out with the integrity departments, to operations, or to any other departments within within the company, in an easy to understand way, one that will inform decisions in a concise way. So before I go on to show some of the examples of how we've been able to combine this data with other outputs from say Pi or visual data analysis, I'll run a short demo of the software so you can actually see it in action. So this is the landing page for the once the software has been loaded with your information. So it tends to be that we would take a download from an IDMS. You're taking all your inspection data for however long it's been gathered for, and upload it in the system. So you can see within this particular demo, which when you go into it, you'll see that we've anonymized the data. We've processed 39 systems, 49 corrosion circuits, over 1,000 lines, and around 12,000 test points. Now you can see that of this, around about 30% of the data, the extreme values that we've identified represents about 30% of the data that we've looked at, which is high. However, we can react to that quite quickly. So even it may be that 100 extreme values are all within the same corrosion circuit, and if we correct an associated piece of data, we can correct 100 of these points. So we can move from this area where it may look like we have quite a high number of values, which with concern around the validity, to a point where we've actually have much higher confidence in the entire data set. So I'll set this running and I'll start to talk you through it. So hopefully this video plays. Here we go. So what we've done is when we're analysing the data, it's often difficult for people to understand what they want to look at first. So we created a number of ways of visualising it to give people a starting point. It's a bit like looking at the internet for the first time. It's knowing what to search for is often the problem. So here what we have is, on the y-axis we have feature types, and on the x-axis we have corrosion circuits. And you can see that as we move the cursor across, the F0 shows that we have no recorded failures. T0 shows we're not using no theoretical data, and we had the final corrosion rate. And as we clicked on that square, we can see that for welds, there was actually only one line that was where we had an accelerated degradation, and when we clicked on that, it was one test point. However, when we click on bends here, we can see that actually it's a far more widespread problem. Actually, we've got quite high, the degradation affecting the whole system. So obviously, immediately giving us an insight into the type of degradation that could be affecting the system. But we may want to then check that against the actions that we're taking. As I was saying, this is about responding correctly to the data. And we can see here what we're actually looking at is per each corrosion circuit, when was the last time it was inspected? So if we have we can see that there's high degradation across the system. Are we actually deploying our resources correctly for them? But equally, we want to just look at something really strikingly obvious with this, that if we now have accurate corrosion rates and remaining lives, what's likely to fail next? So we set this screen up where it looks like we can look at test points that are likely to fail within the next 2 years if that data is proven to be correct, either through reinspection or analysis. And when we click on each of the corrosion circuits, we can then drill down into the lines. And if we were to click on any of those lines, it would show us the test points. It'd take us to exactly those test points where we have that concern. But we may want to look at everything. We may want to look at the entire asset. So we created customizable views all the way through this that allow us to slice and dice the data in any way we want. So in this one, what we'll do is we'll look at the entire, every test point across the asset, and we'll look at all the extreme data that is yet to be sorted and all the trendable data that we have low concern for. And if we can set this up to look at test points, and then we set it up to look at last wall thickness, we can see exactly the distribution of low wall thicknesses across the asset. Now we could set this up, these are absolutes, so like in this context, we would put a limitation on the value, but we could set this up to be relational and check it against nominal to see how much of a threat this poses. But even though it looks like an incredibly dense data set, we can zoom in and we can look on areas of particularly low wall thickness, and we can pick just a single test point. So you can see that very quickly we're going from this incredibly dense data set where you're looking at every wall thickness across the measurement across the asset, to being able to home in on just a single test point that may be causing you concern. And we can choose to view this in any way we want. So as soon as we've selected that, you can see that it's picked up the corrosion circuit, the system, the line, the test point number, and the last wall thickness that we got, had for that reading that we had for that test point. But often you need to think about different ways of interpreting and visualizing the data to make best use of it. So if we were looking at small bore, for instance, looking at it in the same way as we would look at other pipe work wouldn't necessarily give us the same, wouldn't be as useful. So within this visualization, what we've created is three columns where we're looking at the lowest wall thickness reading that was taken for the line, the number of extreme values that we found on it, the number of points of concern that we found for that line, and the time since last inspection. So you can see that on this particular data set, that there's very clearly a line that would draw our attention immediately. 06PT5202 is obviously the one where it has the lowest wall thickness, the most extreme values, and it's the longest time since this inspection. So it directs our attention towards this. So hopefully by now you're starting to see some of the insights that we can gain from mass processing and from actually starting to look at create different visualizations for the data set, but also look at some of the insights that we can get from it. But what I'll do is I'll take you through a couple of case studies where we can compare it with other data, and we can look at what other output we can some other outputs we managed to get from the analysis. Taking using the software as a starting point, but then getting in, try and create some insights into the operation and a little bit of guidance on how we move forward with each of these assets. So for this one, we're going to look at FPSO pipework. So the brief that we had with this particular asset was that to provide confidence in the understanding of the asset integrity status, the operator felt that they had maybe lost control a little bit, and they wanted to be sure that that everything was that they had full confidence in the way that they actually knew where the issues were across the asset. Looking at trying to identify any hotspots and blind spots, and also with this within this project, trying to help define make sure that they had confidence in their late life strategy. One thing that was a particular note with this asset was that they were very clear that their COP was only 5 years away, and they wanted to make sure that any of their actions in the next 5 years were appropriate. It was preceded by another us running another tool that we have where we can run a data harvesting exercise, where we can use automated techniques to actually extract information from reports that haven't yet been put into a database. So we can teach it to look at what to expect within a report, where to look for it within a report, irrespective of its format and irrespective of its file type. So it doesn't really matter if the format changes within the report, or it's Excel, a JPEG, or a Word document, or Excel. We can find that information and transpose it into a tabular format that allows us to carry out analysis. So one of the things that was interesting with this, and it's something that we've actually found that just as a kind of side effect of carrying out this kind of analysis, is that there is a degree of conditioning of the data that precedes the automated analysis that allows us to find issues in the data. And I'll not read from the screen, but you can see quite clearly that there was as much as anything, as well as that analysis, it allowed us to get to a point where we just put we were able to help improve the data management and correct a lot of the inherent problems that were already there, and just make sure that we're a bit better and a bit more effective in the way that we were managing that data going forward. So once we uploaded all the data into the analysis tool and identified the extreme data points, we're also able to plot these on the isometrics as well, which starts to give us a little bit more insight into the degradation patterns, as well as seeing them in the graphs, but actually seeing them in the isometrics allows us to set a priority for the reinspection. Our high priority being the ones that would pose out the analysis would point out were likely to be a high potential for failure. Our medium priority, where they have a higher corrosion rate or shorter remaining life than initially thought, but don't present an immediate risk of failure. Our lower priority, where it was just really about there's doubt over the veracity of the data, but it doesn't look like it presents an immediate threat, or ones that we should look to when it looks like there's a data quality issue and we want to investigate on as a desktop issue and trying to correct that associated data. One of the stretch targets that we had with this project as well was actually to start to look at visual data as well. So we actually, through our data harvesting tools, are actually able to pull out specifics about corrosion categories and then plot these on the PNIDs to see the grouping and to see whether or not there was any patterns that might be about in external degradation that may be dependent upon their exposure to weather, or help to plan FM campaigns and the remediation going forward. And again, always trying to find that efficiency and that point where this has an effect on how you manage the asset, and trying to make sure that it all relates back to the business, to efficiency, and to cost effectiveness in how we maintain the assets. So one of the things that we've got here was it was bringing us back to the point that I made earlier, that that we knew that this asset was going to COP in 5 years. We wanted to make sure that all the actions that were taken in this next 5 years were relevant. So the graph in here, once I explain it, it should become really quite clear. This was when we showed this to the client, they described this as having their entire late life strategy in one graph. And it's proven to be incredibly popular and something that we've created for a number of clients since then. So what we have on the x-axis is the median time since last inspection, on the y-axis the time from last inspection to failure. Now, in the reddish triangle at the bottom of the graph, any circuit that was to fall within that would already have, through analysis, would point out to the fact that it is already consumed. It's already past minimum allowable wall thickness, that it's already consumed its effectively consumed its remaining life. Anything that falls within the yellow triangle would point towards the fact that it's already consumed its half-life. Where you have a grey line, the first of the grey lines across the graph, anything that fell below that line would point to the fact that it would have consumed its minimum allowable wall thickness before COP, and anything that falls below the second grey line would have consumed minimum allowable before COP. So basically anything above that line, you have very high confidence in its remaining life, and the need to be looking at that, or your actions for those systems that are above that line, would seem to be very low. If it's falling in the bottom right hand of the graph, then clearly these are areas that you want to be looking at early. The other thing that you should see as well is that within each of the bubbles actually represents the size of the circuit and the number of lines within the circuit, and the dense dot within it represents the number of lines with inspection data. So we can see that on the left, where we have some quite small but completely dense spots, we can see that actually it might have a relatively short time to failure, that we could be looking at around 3 years before we would have consumed, we would have passed minimum allowable wall thickness. It's actually a relatively short time since we've inspected it, and everything in that circuit has been inspected. So although we know that it has a short remaining life, we have a good knowledge of those systems. Whereas on the right, we can see that actually the time since last inspection for this particular circuit that's been circled is actually pushing 3 years. We only have inspection history for around half of the lines within the circuit, and again looks like it's already consumed its half-life, and we're well towards and it could fail within the life of the asset. So again, very quickly it lets us look where we have the highest concern, where things they have the shortest remaining life, and reflect on our knowledge of that. Whether we have confidence in the condition of the asset of that particular circuit or system. I mean, this is simply another way of looking at much of the same data. So that again, with the when we look at the localized corrosion on the produced oil system, we can see that we can break that down into the lines and their remaining life, and we can plot that against COP, so that we can pick out exactly those lines within that system that look like they have a remaining life shorter than COP. So again, making sure that we direct our actions to the highest criticality areas. So we're making reasonably good time. I wasn't sure whether we get to this point, but I do have time to go over this other pilot study, and this short pilot study that we carried out for an operator. It was actually the preceding piece of work to the analysis of the FPSO. I should leave us plenty of time for questions. So the aim of this pilot was to showcase the potential of what we could do, and looking at our data harvesting and our data analytics. And we had a stretch target to include pie analysis. We were being put up against another system that was using deep learning neural networks to carry out this analysis, rather than a kind of special purpose analysis that we developed. And in the end, we were awarded the contract, and it led on to the the other piece of work that I've just gone through. As I said within this as well, one of the things that we're looking here was to combine the output of our analysis using ADA with PI analysis. And one of the things that we're now working on is a second phase of ADA, which actually has a permanent plug-in to PI. So within this particular system, there was two corrosion circuits that we're looking at, high pressure and low pressure circuits on a water injection system. And the operator had increased their inspection because there had a number of failures. And so we can see that within the graph here that in 2014, the number of wall thickness measurements that was taken jumped up massively because they just lost confidence in the condition of the asset. And we're unsure as to exactly the cause, and assumed that that there was widespread corrosion and erosion issues that could be occurring anywhere on the circuits. So we took all the data as we do normally, and we loaded it into ADA, and we're able to immediately start to extract some information from this. So what we could see that actually, when you just quite simply and quite quickly, that the minimum wall thicknesses, when you distributed them by line, actually had some clear areas that they were affecting, and that the systems weren't being affected in their entirety uniformly, but actually it was in pretty select places within the circuits. And that even though the corrosion coupons were suggesting that there was the corrosion coupons and the pitting rates that had been picked up, absolutely correct, but the assumption was that these were widespread. Now what we were able to show when we looked at this was that actually a couple of things became very clear. When we can see the smaller circle at the bottom, when we investigated that, actually turned out that the pipe spec was wrong within the system, and that nominal was it was thinner than was expected to begin with. So what they were seeing wasn't actually a huge wall loss, but actually the pipework was simply thinner than they expected. And what we were showing in the area that has been the larger red circle around it was that was actually an operational dead leg, and that this system wasn't, and that part of the system wasn't opening up and didn't have anything like the flow that was expected. So what we're actually seeing within this area was MIC issues because of the stagnation within that area. One of the things that we can see here as well is that when we're looking at the PI data, we can see that on the other circuit, that when we're analysing the PI data and we were running time series decomposition on this to actually find some trends within it, but what we were actually looking at was very high flow rates on part of the system. And this actually made sense in both cases, both with the operational dead leg and within this system when we shared this with the process people. The injection was expected to be shared across 6 lines in the system. And what was actually happening was it was being concentrated in just 2 parts of the system. Which meant that that operational bed stayed closed for longer, and 2, that you were experiencing far higher flow rates on these 2 lines. And so again, what we're actually able to show was that this was rather than being a widespread issue, we could tell exactly why it was. It was because of that higher flow rate, and it was concentrated in these 2 lines because the system overall wasn't being operated in the way that it had been intended. Again, we were able to, create very much of the same outputs as we, that you could see that that would be easy for us to produce using the software that we've developed. Showing things like maximum corrosion rates by line and wall thickness by line, or looking at the test points that are likely to fail within the next 2 years, or any of the things that, as you can see, that these are become really quite simple outputs for us. And then inspection efforts versus degradation patterns. So again, we can see that the areas that have been least inspected, in this case it was mainly the small bore tubing that had the lowest inspection, and where we'd actually been inspecting everything else much more thoroughly. But given the presence of MIC that we picked up on, maybe that wasn't appropriate. So hopefully that's given you an insight into some of the things we're doing in data processing and the insight that we can get from it, and why I believe that it can help create these benefits. You know, that we can reduce failures. I think on numerous occasions we've been able to prove that by our analysis highlighting high potential failures on pretty much, you know, on every occasion where we've deployed this, where when the client has gone to look at the areas that we've suggested, they re-inspect. They have confirmed areas of high potential failures. It's often shown that when we've created a better understanding of corrosion rates and remaining lives, that we can readjust the inspection frequency. Clearly, in some cases, that means that there are some things need to be inspected sooner, but overall, what we found is that we generally correct the over-inspection that's plaguing most assets. And you can see, hopefully you can see from the visualizations, that we have a better understanding of asset risks and how we can prioritize inspection and maintenance. So I'll leave it at that, and hopefully take some questions if we have time before we go back to Ruby.
Thank you very much, and thanks for stepping in at short notice for technical issues we were having. We have time for some questions now, and then we're going to take a break, and then Ruby will continue with the remainder of her presentation after that. So I guess there were some questions in the chat in this. But one of them was, is the analysis capability allowing you to move away from so much reliance on RBI and moving more towards a condition-based analysis?
Yeah, it's a really good question, actually. So initially in this first iteration, what it's allowing us to do is to be better informed when we're carrying out our RBI. So it's not about ditching RBI completely, but it's having better analysis and better data to update that. However, what I would say is that using these kind of techniques allows us to form a view that is to understand current condition in the best way that we possibly can, and then from there, what we need to do is look at how we can link that to PI and to understand changes in process conditions and how that can then alert us to concerns. It means that we can be less reliant on inspection and more.
So Ines, just to sorry to interrupt. You mentioned PI in your talk, and now I'm conscious that there'll be some people in the meeting who are not familiar with that.
Oh, sorry.
Maybe we're just explaining what it is.
Yes, absolutely. So PI is a software that's used for monitoring process conditions, and monitoring and modeling process conditions. So it will help you understand fluid composition, temperature, pressure, flow rate, and any of the things that can help that would have an effect on the materials that your pipework, your vessels are made of, and their degradation. So by using ADA to understand current condition and the current condition in your now, that you can then look at taking these other inputs and look to see how you would then look at expected change from your now much improved view on current condition, which allows you to be much smarter in how you manage the asset. So you're moving away from inspecting to remove doubt to inspecting to confirm your expectations.
So yeah, thanks, Ines. And I think that sort of, I guess the next question is relevant to that, around linking to digital twins. And I guess what you're talking about there is really something of a predictive digital twin.
Yeah, absolutely. One of the questions there I can see is that, you know, are we using this to link to digital twin or mini digital twin? The answer is yes, absolutely. Very much see this and the next phase of our analysis capability being linked to visual twins and other information. And so yeah, we are talking to companies about doing that and how we can do that next. I see this and the engine that we're developing as part of the next phase as what gives the modeling capability to a digital twin. A lot of models become a twin when they actually have some simulation capability. And so what we need to be able to do is actually relate this information back to the 3D model and all the properties that are embedded within that, and then allow it to actually, in as close to real time as possible, reflect the degradation of the asset in that model, and allow you to experiment with it and to see how you can change process conditions to actually optimize the maintenance and the running of these assets.
Okay, great. Thanks. Just one sort of technical question, I guess, around the implementation. It's from Niall Dolly, who's asking about, would you use a REST API to connect to OSI PR? You probably know all those acronyms in this.
Yeah, I do. So yes, so OCSoft are the developers of Pi. So the software Pi that is used by practically every oil and gas asset in the world to almost, to monitor the process condition are made by OCSoft. So the API would be application interface. So we're actually looking to see whether we would plug directly to the systems. So we are talking to OCSoft about plugging the two systems together and making them work seamlessly. However, we don't need to do that at the moment. It depends on how quickly you want the update to happen. And to be honest, with the rate of degradation that we would see, doing that on a daily basis would be fine. So we can take a dump from Pi at the moment and upload that sufficiently quickly to give us the kind of prediction that we need.
Okay, great, thank you. And then a question from Seeger was, could you use the analysis of the data to generate the requirements for the NDT? So looking at the improving the overall inspection program.
Yes, absolutely, very much so. It's actually something that we've done quite a bit with this already, because so when you can think of, if you can think about a Bayesian update where you're looking for presence or absence when you've got in your first instance where you're looking. So we have, when you're looking at particular features and the way that they've been degrading, it will direct your NDT towards those particular areas. And because of that, it gives you an insight into the type of degradation as well that you're likely to be seeing, which will help you in your selection of the NDT technique that you would deploy.
Thanks, Dennis. Okay, well, I think we've got time for one final question from Ewan Alphonson. Shell was looking at the data analytics. He's impressed by the data analytics demonstration. And on the fabric maintenance piece, can you pull data to aid prioritization of the piping systems and loops?
Yes, absolutely. It's, as well as we're doing it by test point per system, we can absolutely do it by threat and degradation pattern on the system, and use it not just for the prioritization in terms of going after threats, but in just best use of best deployment of resource. So, for instance, within by taking that extra step with the visualization and plotting it on your PNIDs or other graphics, allows you to see the connection between it. As one integrity engineer pointed out to us, that he'd been specifying FM on particular systems, but hadn't quite actually appreciated the physical relationship between them and the problem that created in terms of logistics and setup. But yeah, it means that we can very much create a prioritized scope around that, and it's one of the things that we've used it for.
Thanks very much, and thank you for that. So I think we'll take a break now, Martin. How long have we? How long should the break be?
Either 10 minutes or 15 minutes, I would think. If we said to come back, would that be all right?
10 minutes probably makes sense, since we're running a bit behind.
Okay, so if we came back at 5 minutes past 3 UK time, that's 5 minutes past 4 Central European time, in 10 minutes, and then we'll carry on with Ruby's talk, the remainder of the second talk from Ruby Roberts. And there's no need to log out of the chat, just mute your microphones, and we look forward to seeing you again in 10 minutes. Thank you very much. Thanks, Dennis. Wonderful talk.
No problem. Thank you.